Thank you very much. Thank you for the opportunity to present our work, joint work with Artem Starikov on typedKanren. So typedKanren, statically typed relational programming with exhaustive matching in Haskell. So a little bit background about miniKanren. So miniKanren is a family of embedded relational programming languages. It was first introduced, I believe, in scheme programming language by William Byrd in his PhD thesis. One interesting feature of miniKanren as a representative of logic programming languages is that it features fair disjunction. That is, the search space is traversed more or less similarly to BFS rather than DFS as it is done in, say, Prolog. Now, miniKanren is embedded and it has implementations in many programming languages, including Clojure, Kotlin, OCaml, Rust, whatever language you prefer. And since it is embedded, one of the cool things about it is relatively easy to bring it for logic programming in actual project. Rather than bringing in heavy standalone logic programming languages. And moreover, there's a version of miniKanren called microKanren, which is a smaller core that can be implemented in most programming languages in one sitting. So you don't even have to reuse an existing implementation. You can do it yourself. And so a quick example of miniKanren is a relational version of appending to lists. So it's list concatenation. Now, since this is a logical programming language and not just a functional programming language, you have relations. So your outputs are also arguments to your relation. So here we have a definition of appendo, a relation between three lists. And this relation basically says that the last list, ZS, is a concatenation of two lists. And you can see the two branches here, what happens if one of the lists is empty and what happens otherwise. Now, the important part, of course, as in any logic programming language, is that you have these modes for arguments, and you can run any relation with unknowns in different parts of the relation. So for example, you can run this concatenation in sort of forward mode in the sense that you have your two input lists and you want to ask what is the result of concatenating them. Or you can give the result of concatenation and then ask, for example, which two lists can provide you with the concatenation that is 1, 2, 3. And then, of course, you will have multiple solutions. And so in general, running these relations will give you a stream of possible answers. Now, typedKanren is a dialect of miniKanren embedded into Haskell specifically. And the main features, I guess, are as follows. So typedKanren supports all of the core functionality of miniKanren, and it supports disequality constraints, which is important for dealing with negative relations, like something is not a member of something, for example. It is statically typed, and it's not just statically typed because Haskell is statically typed. We also have types for relations, and we differentiate between the types of logical variables, and we support user-defined types. And typedKanren offers some support via GHC.Generics and Template Haskell to reduce boilerplate when you want to use your own types. And we offer a thing that we think is relatively novel, which is exhaustive relational matching, which I'll talk about later in the talk. Now, there are already existing miniKanren implementations in Haskell, but most of them are untyped in the sense that they have a type of terms, which is predefined, and then you can only do logical programming within this predefined type of terms. Now, there is another project called Molog, which appears to be unfinished and abandoned, which tried to do the very similar thing to what we have done. So you can compare with that. So here's an example of the same relation appendo written in basic typedKanren. So here we have disjunction of two possibilities, and you can see that every possibility is written with the do notation, where we just specify sequentially the constraints that we have on our input logic variables. For example, in the first branch, we say that X is an empty list. And then if X is empty list, then of course the YS and ZS should be the same. And then in the second branch, we introduce fresh logic variables and then say, well, if the first list is a cons of X and XS prime, and then ZS should also be a cons of X and ZS prime, such that XS prime concatenated with YS gives us ZS prime. Now, the feature that we, sort of one of the distinctive features of typedKanren that we introduce is combinators for relational matching. They're similar to match E in the original Lisp implementations of miniKanren. But beside the typed version of match E that already has been described before, we provide an additional version that also supports exhaustiveness checking, making sure that we have covered all the constructors that are present in the user-defined type. Now, to the best of our knowledge, none of the existing types implementations of miniKanren have even support of the match E, never mind the exhaustive version. So here's an example again of the same appendo, but now defined with matching. So here we're using exhaustive relational matching with this match E prime combinator, and access is given to this match E, so we're matching on access, and then there are two patterns, both of which are prefixed with this on prime combinator. So we're checking if the input list is, if XS is empty, then YS should be equal to ZS. And if XS is a cons, and these are the components of that cons, then we introduce a fresh variable ZS prime, make sure that it's a cons, and make sure that XS prime plus YS, it gives us ZS prime. The final thing, enter, just wrapped around. So as you can see, this is not a built-in case that we are able to use here. We have to use our own sort of set of combinators. Match E sort of completes matching on one side, and enter starts this pattern matching on the other side. And so everything in between are the branches that we are pattern matching on. So to briefly talk about the core of typedKanren, from the user perspective, typedKanren consists of the logical type class. This is a type class that specifies a logical counterpart for any given type, as well as necessary methods for the typedKanren to be able to do the unification and search. There's a goal monad, which is a context in which relations are combined, as you have seen the do notation used in the previous slides. And there are, of course, utilities to reduce boilerplate for the logical type class. So to understand why we need this logical types versus regular types, this is a problem that occurs specifically in a typed, statically typed setting. So for example, if we have a tree data type on the left, if we want to use that trees in a logical program, now we need to specify which subterms of this tree are allowed to be unification variables or logic variables that are going to be learned about in the process of unification inside of the logical engine. Now, for that to work, we need to replace these subterms, and by default, for example, we can replace every subterm with the type term parameterized by the original type. And what this does is it says that we either have a value of type A there, or we have a unification variable. For recursive use of tree A, it's a bit more subtle than that, because we don't just want to have a tree A or unification variable. We want to have a tree A where, again, in any of the sub expressions, we can also have unification variables. So how the term is essentially described as a sum type, where it is either a unification variable or it's a logical counterpart of the original type A. And so the logical counterpart comes from an associated type family from a logical type class. And we demand that from this logical type family, we can uniquely determine which time this originated from. This is not a data family for technical reasons, but this is one of the design choices that we've made. And there are a bunch of methods here that define how to properly do the unification, how to check the occurrence of recursive occurrence of the unification variables inside, etc., etc. Now, importantly, most of this can be done automatically via GHC.Generics. So the instance can be derived via GHC.Generics, and the type can be constructed using Template Haskell. So here's an example of an instance of logical instance for a tree. So we do here. What we do here is we define the logic counterpart of tree is going to be L3A that we have seen before, and then there is a standard definition for all of the methods. So the Go monad, where we combine the computation, follows the standard implementation in all of the miniKanren, all of the other miniKanren implementations, with a minor difference that we actually turn the Go monad, from a function from a state to a stream of states to an actual monad by adding the result in the end in the stream as well. Now, this is helpful for several reasons. One is generating fresh unification variables is a part of, works inside of a Go, and the new variable is returned. That's going to be the result. But also this enables the use of the do notation, which makes writing some of the typedKanren programs very concise. So streams here are specifically the so-called immature streams that are either done or yield something, or they await the result. So the await here is important for the fair search strategy in typedKanren, so that we can do sort of a BFS on all of the branching that happens inside of the relations. And the state, just to make it clear, it consists of the known substitutions for variables at the moment. It also contains the disequalities, which are constraints on what certain unification variables should not be equal to. And this is important because, unlike Prolog, with miniKanren, we cannot do negation as failure, and instead negation is done through these disequality constraints. And there is a max var ID just to keep track of the last available identifier for fresh variables. So here's again an example of a relational program in, this is an example of a functional program on trees that counts the number of, collects all of the leaves in a tree. And as you can see, this is written very, very easily with the case here. Now, we can write this with a disjunction and then specify each possibility in a separate branch. Instead of pattern matching, we're going to have these unification constraints, which are written immediately as statements in a do notation. This is the code that is equivalent to what we have seen on the left. Now, we can run, again, this program forwards, like we've seen before, or we can run and we can convert the logical results. We can also extract or try to extract them into the actual Haskell value, so that we can convert, so inject here converts the Haskell value into the logical counterpart, and extract converts it back from logical counterpart to Haskell variant. And of course, we can run the same backwards, where we say, well, if the leaves are 1 and 2, which trees can have these as this set of leaves? So it works in either direction. Now, I want to talk very briefly, I guess, about relational matching. The main idea is that we would love to use the case expression that is built into Haskell, but unfortunately, the matching in a relational way should not only be able to work in one direction. It should also be able to generate all of the cases if the input variable is unknown. And for that, we could not have figured out how to reuse case in some clever way. So instead, we have borrowed an idea from a total library by Gabriela Gonzalez, where prisms are used instead to have a sort of total version of case, but with arbitrary constructors like prisms. Right. So I'm gonna show just a very simple example here. We have a result AB, and we have prisms OK and fail for that to pattern match as a sort of first class patterns for the result data type. And then to enable relational matching, we specify match E that takes a term and tries to pattern match on it. And by default, match E doesn't have any alternatives. And then we can add on these alternatives or patterns with a specific combinator called on, which takes as one of its arguments a matching for all of the other alternatives, and it just adds one more alternative with a given prism and a given handler for what to do if that prism actually works. And so in the end, we get an extended matching with one more alternative. So for example, again, the example with leaves will work something like this, where we specify each alternative using on. Now, this version of match E works, but it does not. But it is not total. It doesn't check that we have actually verified all of the constructors. And for relational programming in general, this is fine. But sometimes you still want to make sure that for a particular version, you have traversed all of the possibilities. So for that, we introduce exhaustive prisms, which are variants that are tagged by some information that's tracked on the type level for tracking exhaustiveness. And again, this trick is essentially a variation of what happens in the total library. And so we define our own versions of these prisms, which then specify so logic leaf in particular is a prism that works with L3. And then we have a version of on that specifies the same thing, but it now converts some of the type information, and specifically it converts the cases from remaining to checked once we introduce a certain prism. And we have versions of match E and enter, and match E now has this type class constraint exhausted, which verifies that all of the patterns have been matched. So, and again, here's just a quick example of how that would work. I'm gonna skip this type information just to avoid getting overtime, and I just want to talk one last thing about performance evaluation of the typedKanren. Now we have compared our performance of our implementation against faster miniKanren, which is the standard implementation in Racket. This is the default one that is used. There's also oKanren, a typed version of miniKanren embedded in OCaml. And there's also KLogic, also a typed version, but embedded in Kotlin. So we have compared this using relational programming for arithmetic and Quine generation, so generation of programmers in programs in Scheme. And the results are as follows. The fastest implementation is remains to be the faster miniKanren, the Racket one. The other ones are significantly behind. And our implementation fares more or less against K-logic, and it's slightly slower than O-Kanren, at least on these examples. But you can see that, for example, for Thrines, our implementation degrades much faster than we would love it to. Now, for the performance, we have tried several approaches to improve it, and in particular, there's an interesting approach that O-Kanren takes to improve performance that, unfortunately, due to the laziness in Haskell, is not really transferable to us. So I'm not going to get into the details of that, but just going to mention that there is something interesting to be done about performance that we have not yet been able to do. And if you're interested in helping us figure that out, you're welcome. So in conclusion, we have an embedding of miniKanren in Haskell, a statically typed statically typed version of miniKanren. We support user-defined types. We provide the type version of match E using prisms, and of course, an exhaustive version of that. We assist the user with generating logic types with metaprogramming tools built on top of Template Haskell and GHC.Generics. There are a few things that we would love typedKanren to obtain, but perhaps the most important one that I'm going to focus on today is the performance. We are sort of a little bit out of ideas of what prevents Haskell from being on par with OCaml or Racket. If you're interested in this project and would like to help us figure that out, just contact us. So that's going to be it. Thank you very much, and I'm open to questions if there's any time for that.
Any questions?
And at the moment, I cannot hear any of you.
Hey, can you hear me?
Yes, I can hear you now. Thank you.
You were lamenting earlier that you can't use an actual Haskell case statement for the pattern matching. Since you're already using Template Haskell for other stuff in the library, could you have some kind of Template Haskell construct where you write a case and then
Yes.
it transforms that into the code you showed with the match operators?
Yeah, absolutely. So there are two things to say about this. First is quasi-quotation is possible, and we can of course offer any syntax, including case inside of quasi-quotation, to make that work. But we're hesitant to do that because we wanted at least the first version of typedKanren to not enforce the use of Template Haskell on the user. So this is why we went in the direction of exploring prisms instead. But yes, definitely Template Haskell can be used there. Another way that Template Haskell can be used here is to go one step further and automatically convert existing functional programs with case in particular into their relational counterparts. So if you have already an implementation of append, you could automatically turn that using Template Haskell into a relational version. So that, of course, also would help tremendously. But again, this is already pre-processing of code rather than exposing the user to purely Haskell primitives.
Right, yeah, that makes sense.
But that's definitely a future work.
Let's take one more question.
Does it support concurrent evaluation of relational programs? Like sharing the same variables?
So there should not be a problem here because so we have the states which are purely functional. It can be shared easily. We did not try to run the proof search in parallel, if that's what your question is.
Well, I mean, the user could decide what parts of the program they want to run in parallel.
Right. So the user here runs these relations through a specific combinator called run. And within this run, all of the unification variables are local to that specific execution. So you can have multiple concurrent threads in Haskell, and everything will work. And you can run this separate. So unification variables are not global, if that's
No, I mean, what
maybe
I
what
want
you were
is to
asking.
have two threads that are sharing the same unification variables. So one thread could, say, bind part of a structure, and another thread could bind a different part of that structure.
Right. Okay, I see. No, that I think is would not work out of the box. No, I don't think so.
Okay, thanks.
Maybe we can take more discussions offline. All right, let's thank
Yep.
the speaker again.
Thank you very much.